Imagine this. It's the 1850s. You hold a small, shiny piece of metal. It's light, strong, and it doesn't rust. You might think it's just some common metal today, but back then, this metal was worth more than gold. People made jewelry from it. Kings used it for their special dinner plates. This metal was aluminum. It sounds strange, right? We know aluminum is a cheap everyday material now, but a century and a half ago, it was a miracle, a treasure, and an absolute luxury. To understand why aluminum was so special in the 1850s, you first have to understand what it meant to be a metal back then. And it starts with a simple fact: aluminum is everywhere. It's the most common metal in the Earth's crust. Think about dirt, clay, rocks, a lot of that stuff has aluminum in it. But here's the problem: it's almost never found on its own. It's always mixed up with other things, locked tightly into compounds. Gold, on the other hand, is rare. You have to dig for it, sift through riverbeds, or mine deep underground. But when you find gold, it's usually just gold. It's pure. You can pick it up, melt it down, and use it. People have been doing this for thousands of years. The process for getting gold is pretty straightforward. You find the nuggets or flakes, you wash away the dirt, and you've got your valuable metal. Even a child could learn to pan for gold. This natural purity made gold easy to get, relatively speaking, once you found it. The aluminum was different. Nobody in the 1850s was going to stumble upon a chunk of pure aluminum. It just doesn't exist that way in nature. It's always bonded with oxygen and other elements, making tough, stable minerals. Think of something like bauxite, which is the main ore we use today. It looks like reddish clay. Back then, chemists knew aluminum was in there, a key part of many common clays and minerals. They knew it was abundant in the ground, but they just couldn't get it out. The chemical knowledge of the time was good, but it wasn't advanced enough for aluminum. Imagine trying to pull two super strong magnets apart that are stuck together, but you only have a tiny weak magnet to do it with. That's a bit like what it was trying to separate aluminum from its oxygen. Aluminum holds onto oxygen with an incredibly strong bond. It takes a lot of energy to break that bond, and it takes very specific chemical reactions. In the 1850s, chemistry was still figuring out a lot of basic things. Scientists were just starting to understand the elements in a systematic way. They didn't have the tools or the deep understanding of chemical bonds that we have now. They couldn't just throw a strong electric current at it, for example, because reliable, powerful electricity wasn't readily available for industrial use. That kind of technology was still decades away, so even though aluminum was everywhere, it was effectively invisible. It was trapped. It was like knowing there's a huge treasure chest at the bottom of the ocean, but you don't have a submarine or even a boat strong enough to reach it. The treasure is there in huge quantities, but it's completely inaccessible. This inaccessibility was the first and most important reason for its extreme value. This gold was rare but obtainable. Aluminum was abundant but unobtainable, and in the world of high-value goods, unobtainability often trumps natural rarity. If you can't get it, it becomes infinitely precious. Scientists had tried for years, even decades, to isolate aluminum. They knew it was a distinct element, they even gave it a name, but all their efforts yielded only tiny specks, bits of powder, or impure blobs. These were scientific curiosities, not usable metal. They were incredible achievements for a lab, but they weren't enough to make a spoon, let alone a crown. So, the metal was understood to exist. It was known to be abundant in the Earth's crust, but nobody had figured out a practical, or even semi-practical, way to separate it from its sticky chemical partners. That's why, in the middle of the 19th century, a tiny piece of aluminum represented a monumental triumph of science, and its price reflected that incredible effort and rarity. Getting aluminum out of its natural compounds was a huge challenge. For years, it was more of a theoretical idea than a practical one. But chemists kept trying, and eventually small breakthroughs started happening, though they were still a long way from making aluminum cheap. One of the first significant steps was taken by a Danish chemist named H.C. Ørsted in 1825. He managed to produce a tiny amount of aluminum. It wasn't a solid, shiny chunk, but more like an impure powder. He did it by reacting aluminum chloride with an amalgam of potassium. An amalgam is like a paste of metal and mercury. It was a very tricky process, and it only produced a few tiny particles. It was a proof of concept, showing that it could be done, but it wasn't a method for making anything useful. It was a true lab experiment, a scientific curiosity, not a path to industrial production. A few years later, in 1827, a German chemist named Friedrich Wöhler improved on Ørsted's work. Wöhler skipped the mercury and just reacted anhydrous aluminum chloride directly with potassium. He heated these chemicals together in a crucible. This was a very dangerous process. Potassium is an extremely reactive metal, and heating it with other chemicals can cause explosions. But Wohler succeeded in getting small, pure beads of aluminum. These beads were still very small, like pinheads. He refined his method over the years, and by 1845, he was able to produce enough of these tiny aluminum beads to study their properties a bit better. This was a big deal. For the first time, scientists could examine some of the actual characteristics of aluminum metal. They saw it was light, silvery, and didn't tarnish easily. These early observations fueled the excitement. This metal had amazing qualities, but it was still incredibly hard to get. The real shift towards something slightly more practical came in the mid-1850s with a French chemist named Henri Etienne Sainte-Claire Deville. He was a brilliant scientist, and he dedicated himself to finding a better way to produce aluminum. Deville knew that potassium was too expensive and too dangerous to use on any larger scale. So, he looked for an alternative. He focused on sodium. Sodium is also a very reactive metal, similar to potassium, but it was slightly cheaper and a bit easier to handle, though still incredibly difficult and dangerous to produce at the time. Deville's process, developed around 1854 and 1855, involved reacting aluminum chloride with metallic sodium. He would heat these two substances in a special furnace, sometimes adding a flux like cryolite, another mineral, to help the reaction along and collect the molten aluminum. This was a crucial step forward. It was still very complicated and expensive. Think about it, you needed to produce metallic sodium first, which was itself a cutting-edge, difficult industrial process back then. Sodium was made by heating sodium carbonate with charcoal at extremely high temperatures in iron retorts, a process full of challenges and dangers. Then, you needed to make pure aluminum chloride, which also wasn't simple, and then you had to combine these two highly reactive chemicals under controlled high-temperature conditions. The scale of Deville's production was still small by today's standards, but it was a massive improvement over Wohler's pinhead beads. Deville could produce ounces, sometimes even pounds, of aluminum at a time. This was enough to start making small objects. But the cost was immense. Every single step of the process was labor-intensive, required expensive chemicals, consumed huge amounts of fuel for heating, and was quite hazardous. Imagine a small factory where highly skilled chemists and technicians were carefully handling dangerous, volatile materials under extreme heat. Every ounce of aluminum produced represented a huge investment in materials, labor, and scientific expertise. So while Deville's process was a breakthrough, it didn't suddenly make aluminum cheap. It's far from it. It just made it possible to get a usable quantity of the metal, but at a staggering cost. The production of aluminum was less like mining for gold and more like trying to synthesize a rare diamond from scratch in a very inefficient and dangerous lab. This intense difficulty and high cost of production were the primary drivers of aluminum's incredible value in the 1850s. It was a testament to human ingenuity, but also a stark reminder of the limitations of technology at the time. Because aluminum was so incredibly hard and costly to produce, it became an ultimate luxury item. And it wasn't just expensive, it was exclusive. Only the very wealthy, or those with special connections, could own anything made of aluminum. In the 1850s, aluminum was a symbol of incredible prestige, much more so than gold, which had been around for millennia and was relatively well understood. Think about it. Gold was valuable, sure. People made jewelry, coins, and decorations from gold. But everyone knew what gold was. It was a known quantity. Aluminum, though, was new. It was a marvel of modern chemistry. It represented the cutting edge of science and technology. To own something made of aluminum wasn't just a display of wealth. It was a display of advanced taste and an appreciation for scientific progress. It was exotic, truly rare. The most famous example of aluminum status comes from France, particularly with Emperor Napoleon III. He was very interested in new technologies and saw the potential in this lightweight, non-corroding metal. He understood that it might have military applications in the future, perhaps for making light armor or helmets. He became a patron of Henri Deville and supported his efforts to produce aluminum. This imperial backing immediately elevated aluminum to an even higher status. Napoleon III famously had aluminum cutlery made for his most esteemed guests at banquets. The story goes that the emperor himself and his most important visitors were served with aluminum forks and spoons, while guests of lesser standing had to use gold or silver cutlery. Imagine that! Gold and silver were common enough to be used by the lower ranks at the imperial table, but aluminum was reserved for the true elite. This really highlights how highly it was regarded. It wasn't about the monetary value alone, it was about the absolute exclusivity and novelty. Deville even displayed aluminum at the 1855 Paris Exposition, a huge World's Fair showcasing technological and artistic achievements. Aluminum was presented there as clay silver, a new precious metal. It sat alongside the French crown jewels, drawing crowds and sparking wonder. People were fascinated by its lightness and its silvery shine. It looked beautiful, and it felt impossibly light compared to silver. It was a metal that seemed to defy expectations. Another powerful symbol of aluminum's value in this era is found across the Atlantic in the United States. When the Washington Monument was being built, its capstone, the very tip of the monument, needed to be something special. It needed to be resistant to the elements, strong, and it had to represent the pinnacle of American engineering. In 1884, a 100-ounce pyramid of pure aluminum was chosen for the apex of the monument. This was a massive piece of aluminum for its time, especially for such a highly refined and pure sample. It cost a fortune more than the equivalent weight in gold or silver would have cost at that moment. The choice of aluminum wasn't just for its practical properties, though its resistance to tarnishing was a factor. It was chosen because it was the most modern, most technologically advanced, and most prestigious metal available. It was a statement. It screamed progress and innovation. So, in the 1850s, aluminum wasn't just a metal. It was a marvel. It was the new gold, but even more exclusive because of how incredibly difficult it was to get. It wasn't something you could just buy with money. It was something that required immense scientific effort and often the backing of powerful figures. Its lightweight, its silvery luster, and its resistance to corrosion were impressive, but the real source of its value was the sheer human ingenuity and persistent struggle it took to bring it into existence. It was the ultimate status symbol, a metal that proclaimed, "We can conquer even the most stubborn chemical bonds." The economic reality of aluminum in the 1850s was stark. Its price was driven entirely by the exorbitant cost of its production. It wasn't about market speculation or supply and demand in the way we think of gold. It was about raw material costs, energy, labor, and the immense scientific expertise required. Let's look at the numbers, and they are sometimes tricky because of how quickly things change and how small the quantities were. But here's the general picture when DeVille first started producing aluminum in tiny quantities in the early 1850s. Before he refined his process, the cost could be as high as $1,200 per pound. To put that in perspective, gold was around $200 per pound at that time. So, for a brief period, aluminum was literally 6 times more expensive per pound than gold. It was an astronomical price. This was before the process was even slightly scaled up, when it was still very much a laboratory triumph. As DeVille improved his method and industrial techniques for making sodium became slightly better, the price of aluminum started to come down, but it was still incredibly high. By 1859, after several years of refinement, DeVille managed to bring the price down to about $17 per ounce. Gold was then about $19 per ounce. So, by the end of the decade, aluminum was still incredibly expensive, comparable to gold on a per ounce basis, and still far more difficult to acquire in any quantity. To understand why this was, consider DeVille's process again. You needed pure aluminum chloride. You needed metallic sodium. Making sodium was a big deal. It involved reducing sodium carbonate with charcoal at very high temperatures. Imagine how much fuel that consumed, how much labor was involved in maintaining those furnaces, separating the sodium, and then carefully storing it, because sodium reacts violently with water and air. This wasn't a push-button operation. This was skilled labor, dangerous work, and constant attention. Then you had to combine this expensive reactive sodium with the equally carefully prepared aluminum chloride. This was all done in specialized high-temperature furnaces. The equipment itself was costly to build and maintain. The yield of aluminum from the reaction was not 100%. There were losses. Every step was costly, from the raw minerals used to make the sodium and aluminum chloride, to the heat sources, to the wages of the chemists and workers. The gold, on the other hand, had a long-established value system. Its price was influenced by mining efforts, new discoveries like the California Gold Rush that started in 1848, and its role as currency and a store of wealth. While finding gold could be hard work, the extraction itself, once it was found, was relatively simple. You didn't need a complex chemical factory. You just needed to melt it down and refine it. The market for gold was global and robust. Everyone understood its value, and it was relatively easy to trade. The market for aluminum was tiny, almost non-existent for everyday consumers. It was mostly driven by scientific curiosity, government patronage like Napoleon III, and a few very wealthy individuals who wanted the ultimate status symbol. There wasn't a widespread demand because it was simply too expensive and too rare to be practical for anything other than showpieces. Its value was not based on inherent scarcity in the earth, but on the artificially created scarcity due to technological limitations. No one could just go and find aluminum. You had to have it made at immense cost. This made it a unique economic beast in the 1850s, a metal whose price reflected not its natural abundance, but the incredible effort required to tame it. The reign of aluminum as a super precious metal was brief. It was a unique window in history driven by a specific set of technological limitations. Once those limitations were overcome, its value plummeted dramatically, reshaping the industrial world forever. The big change came in 1886, about 30 years after DeVille's breakthroughs. Two young men working independently and on opposite sides of the Atlantic, Charles Martin Hall in the United States and Paul Héroult in France, discovered virtually the same process. This was the Hall-Héroult process. This new method used electrolysis. They dissolved aluminum oxide, the purified form of bauxite, in molten cryolite, and then passed a powerful electric current through it. The electricity broke the strong bond between aluminum and oxygen, separating the pure aluminum metal. This was a game changer. Why? Because by the late 19th century, large-scale, affordable electricity was becoming a reality. The Hall-Héroult process was energy-intensive, but with the advent of large electric generators and hydroelectric power, that energy became much cheaper and more accessible. It eliminated the need for expensive and dangerous metallic sodium. It was a continuous process, meaning you could produce aluminum in much larger quantities and with much less labor per unit. The results were immediate and dramatic. Aluminum went from being a metal worth more than gold to something much cheaper than silver, then eventually cheaper than copper. Its price dropped from $17 an ounce to just pennies an ounce in a matter of decades. This sudden availability meant that aluminum could finally be used for all the things people dreamed of: lightweight parts for cars and airplanes, durable cooking pots, foil, and eventually soda cans. It became the ubiquitous, everyday metal we know today. Its value shifted from being a symbol of scientific triumph to a symbol of industrial efficiency and utility. But gold's value never really changed in that way. Gold's value isn't based on the difficulty of its chemical extraction since it's found pure. Its value comes from its natural scarcity, its unique properties, it doesn't corrode, it's easy to work with, it conducts electricity, and its deep historical role as a currency, a store of wealth, and a symbol of adornment. People have valued gold for thousands of years, long before modern chemistry, and they continue to value it today. Gold doesn't get cheaper when a new extraction method is found, because its value isn't tied to extraction difficulty, but to its finite supply on Earth and its perceived worth across cultures and economies. So, in the 1850s, aluminum was more valuable than gold not because it was intrinsically rarer in the Earth's crust, but because it was technologically inaccessible. It was a triumph of human effort against stubborn chemical bonds. It was a new shiny marvel that only the most advanced scientists and the wealthiest patrons could bring into existence. Gold, for all its timeless appeal and scarcity, simply didn't present the same kind of scientific challenge. It was a known quantity. Aluminum was the future, a hard-won glimpse of what human ingenuity could achieve. But that glimpse was expensive, fleeting, and based on limitations that were destined to be overcome, forever changing its place in the world of metals.